Buenos días a todos y todas las presentes en la sala y a aquellos que nos acompañáis a través de la red. Hoy contamos con la presencia del profesor Niels Lund, quien nos va a hablar sobre las técnicas observacionales en la astronomía de rayos X y rayos gamma. El profesor Lund lleva 4 décadas trabajando en este campo, es decir, desde los orígenes del campo en sí. En la segunda década de los años 60 participó en el diseño y lanzamiento de más de 20 instrumentos en globos aerostáticos, antes del comienzo de la era de los cohetes y de las misiones espaciales. En 1971 fue coinvestigador de una de las primeras misiones espaciales para el estudio de las fuentes astronómicas de alta energía, GAO-3, y desde entonces hasta la actualidad no ha dejado de trabajar en diversos detectores, siendo investigador principal de los instrumentos Eureka y Granat en Watch y de Yemes en Integral. Durante su dilatada carrera ha formado parte de diversos comités de estudio de misiones de la Agencia Europea del Espacio y ha publicado más de un centenar de publicaciones. Les dejo pues con el profesor Niels.
Thank you very much, Sylvia, and I'd like to thank the astronomy group here at Alicante University for inviting me for staying here a couple of nice months in the spring, and we have been having a very good collaboration, and I'm sure we will continue this in the years to come. Of course, also this collaboration actually goes back 10 years already. Sylvia spent a couple of years in Copenhagen 10 years ago. So today I'm going to tell you about some of the problems we have when we want to study X and gamma rays from space. So let us start. Let's see if we can move forward. We have astronomy is now covering an enormous range of wavelengths. It's very surprising that astronomy started out in a very narrow little window here, the visible window, which we can see with our eyes and the optical telescopes can see. And this window actually was all astronomy produced up until say 1930, 1940. Then in the 1930s and 40s, people began also to investigate the radio window. The atmosphere of the Earth is not transparent to most of the wavelengths in the electromagnetic spectrum. Only at the visible and in the radio, and a few narrow bands also in the infrared are opened so that one can look through the atmosphere. For the rest of the astronomy, one have to go to space, except again within the last 20 years or so, one have found that it is possible also to do astronomy at the very highest energies, gamma-ray astronomy, at the very highest energy from the ground, and I will spend some time describing this because this is one of the most important developments in gamma-ray astronomy, that this window out here at extremely high energies have been opened. So, I'd like to spend a few minutes in the beginning just to mention how do these photons arise, from where will the X and gamma-ray photons come, and there are a few processes which we should know. When we start considering photons at the lower end X-ray energy, say 1 keV to 100 keV, then the dominant process is the same process we know from optical astronomy. It is a thermal emission from hot bodies. But in this case, in order to reach energies above 1 keV, you need temperatures up in the 1 to 100 million degree range, And actually such temperatures looked completely impossible before the space age. It was a big surprise for astronomers when the space age started that there actually were X-ray sources in the sky. It was unexpected. One knew that the sun could emit X-rays and gamma rays during explosive solar flares, but it was impossible to imagine that a star could maintain a temperature of 10 or 100 million degrees, because with such a surface temperature on a star, the star would use up all its energy in just, in a few million years. It would, or even less than that, maybe in a few years. And so it was an impossibility for the astronomers to imagine that there were any X-ray stars. But when the first rocket experiments were made, not looking for X-rays from the stars, but looking for X-rays from the moon, then suddenly it was discovered that the sky was full of X-ray sources. And then, of course, one had to revisit the ideas, why could this be possible? And it was then soon realized that if you have very small bodies, such as compact objects, neutron stars and black holes, then the dimensions of the emitting region is so small that despite the very high temperature, the total amount of energy radiated is not larger than, say, the energy emission from normal or large stars. When we go to higher energies, of between 100 keV and 10 MeV, then this is the region where atomic nuclei, radioactive atomic nuclei, they emit many gamma rays in this regime. And this is, of course, a very interesting possibility that we could use the gamma ray lines to identify nuclei in such very hot environments. And we could test our ideas about nuclear synthesis in stars. There's also a strong line from electron, positron annihilation, which give rise to a half an MeV line. And so this is a potentially very rich field, but as we shall see a little later, it's an extremely difficult field to work in. Then when we come to energies above 10 MeV, then essentially we are now looking at photons which arise due to energetic particles, cosmic rays as we would call them. Most of the emissions are from electrons interacting with other matter or with magnetic fields, but also nuclei can give rise to gamma rays at the higher energies. So these photons above 10 MeV, they are pointing us to the regions where we have acceleration of particles, that is cosmic ray sites. Now, how do we then detect the photons? This was a little bit about where they come from. Now, how do we detect them? Because my talk is about experimental techniques rather than all the interesting science you can do with these photons. I'm very much concerned with what are the interactions between photons when they arrive at our instruments and the instruments. So how do we detect them? If we start again at the lower energies, then photoelectric absorption is the dominant process. If a photon arrives with an energy of 1, 10, maybe up to 100 keV arrives, then the typical interaction is photoelectric absorption, the photon hits an atom, knocks out an electron, and the photon is gone. It has deposited all its energy to that electron and to the hole in the electron shell in the atom. So it is a very local process. The photon is detected in a microscopic point. The next, when we go to slightly higher energies, say around 1 MeV or so, then the typical interaction is Compton collision, where the photon is hitting an electron, and what one can say is that the photoelectron absorption almost always happens at the most strongly bound electron in the atom, because the photoelectron absorption involves also the interaction with the atomic nuclei. It can only happen, so to say, on a bound electron. But Compton collision can happen with any electron. So essentially, since we are also dealing with higher energies, the electron can be considered as free. We can neglect the fact that the electron belongs to an atom. And Compton collision, the photon does not disappear. It's making a scattering, delivering some energy, and then the photon is continuing its travel with a lower energy. Eventually, it may make another Compton collision or a photoelectric absorption, so it may in the end be absorbed, but it could also just go away from our instrument, leaving a part of its energy to the electron it struck. And then there is a third important detection way, and that is the pair creation. If a photon with high energy, at least half an MeV, but typically higher than that, comes in, and it can interact in the field of the atomic nucleus, and it will create a pair, an electron-positron pair. That requires half an MeV, so that's why it's a minimum requirement that the photon has half an MeV. But then the rest of the photon energy is given to the kinetic energy of these two electrons, to this pair. And this process is dominant at the higher energies. So if we look, for instance, if the material we look at is air, we usually don't make our instruments of air, but it's anyway interesting because these extremely high energy air showers, they are, so to say, generated in air. So it's interesting to look at air as an example of a mixture, of course, and primarily nitrogen and oxygen. And we can see here that photoabsorption is this steep curve here, which essentially disappears around 100 keV, 0.1 MeV, and it has a very steeply falling cross-section with increasing energy. Then Compton collision is this smooth curve, which has a rather flat maximum around 1 MeV. And then the pair creation comes up over here. And then the total is this wavy curve here. If we look at a more typical detector instrument, you can say, namely lead, we prefer to use heavy atoms in our detectors because they are more effective in stopping, the photons. And I should maybe point out that compared to the previous slide, the scale, you see this scale goes to 10 here, but the next scale of lead goes much higher. So goes up to more than 100. You see again the photoelectric absorption, it has some kinks now because it dependent on which electron it is interacting with. But again, it has this very steeply falling cross section, and the pair creation comes up here, and then the Compton is lying down here. So the Compton interaction in lead is is only dominating in a relatively narrow range of energies. It is either pair or photoelectron, which is a typical interaction type. Now, as an illustration of the technical difficulties of doing astronomy in different energy ranges, I have taken here a list of the number of known sources at various energies. And you can see that in the low energy range, where we can use telescopes similar to optical telescopes, focusing telescopes, we can make X-ray mirrors in this energy range with some ease, and this we have been able to do this for 30 years or so. So in this energy range, the number of sources is high, very high, 100,000 maybe, and so there are lots of sources known here. As soon as we come above the range where mirror telescopes can be used, the number of sources drop very dramatically, say to around 500 in the 10 to 100 keV range, maybe 200 above 100 keV, and to a scant 30 sources or so in the range between 1 MeV and 30 MeV. I shall come back to why this is such a terribly difficult region, but you saw the absorption curves, and the absorption curves had a minimum there, and that is essentially the problem. It's very difficult to make an effective detector for 30 MeV or for 10 MeV photons. And then, as you come higher, the pair creation process comes in. It has higher cross-section, and also the fact that the outgoing electrons have higher energies make it easier to detect them. So the number of sources here is now higher than 1,000, and then as we come to the even higher energies, the ground-based air Cherenkov telescopes are now also finding many sources, and probably today even more than 150. It's getting up quite rapidly, the number of sources we can see at the highest energies. But there is this very difficult region between 1 and 30 MeV where we are in big troubles. So, this is again, this is the same story. Below 10 kV, classical X-ray astronomy, classical in the sense it was started with the mirror telescope and Einstein, then there was Exosat and there was Rosat, there were many mirror missions, and they made a lot of source discoveries, and they could make detailed studies of the morphology. Most X-ray sources are point sources, but there are some which are extended, and where we can actually make morphological studies on how the X-rays are emitted. Say, supernova remnants is one case of an extended source where it is of great interest to study where is the most active X-ray emitting region, and it is in the shell, at the edge of the shell, where the supernova material is colliding with the surrounding interstellar medium. When we go to high energies, 10 to 100 keV, then it is mostly relatively primitive collimated detectors. That is a detector which with essentially a cardboard or a LED tube in front of it, so we can only see a small section on the sky. Or it is more advanced and typical today, the coated mask instrument. That is, you have a mask with holes. I will describe that also in more detail a little later. So there are techniques here, but they are not focusing. And because they are not focusing, the sensitivity is limited. However, just now, last year, the first space mission with a focusing mirror extending up to about 80 kV has been launched, and is providing the first results. And again, up to 1 MeV, it is still the coded collimators and the coded mask telescopes. We may push our focusing telescopes up into this range, but it has not yet been done. Then when we come higher, this is this difficult range, 1 MeV to 30 MeV, and a number of experiments have been done. COMTEL has flown on the Gamma-Ray Observatory and has given us the first maps of the sky, you can say, and there are future wishes, birds on the roof, you can say, the advanced Compton telescope, which may improve on the situation here, but it is a difficult. And then, when we come to the higher energy, it's 30 MeV to 100 GeV, the pair telescope, very massive, big satellite experiments, Agile and Fermi are now flying, and prior to that, COSB and the SAS satellite, the NASA SAS satellite, that's to investigate this week. And then here, at the highest energies, we have the ground-based telescopes like HESS and Milagro and others which I will mention. So the challenge for gamma-ray astronomy is that at energies above 1 MeV, the particle flux is always much larger than the gamma-ray flux. So you're sitting in a hailstorm of particles, high-energy cosmic rays, which are bombarding your instrument, and how do you single out a few gamma rays from this hailstorm of particles? We have a high background, and of course this, and for space instruments, therefore, sitting in this hailstorm of particles, you have to worry about what materials you put into your instrument, because all the materials will get radioactive. So your instruments will begin to shine in exactly those gamma rays you want to study from the sky. And that is a very unpleasant situation, that your own instrument is emitting the types of radiation you want to study. And both of these problems here could be lessened if we found ways of focusing the gamma rays, and this is why there is so much interest in such techniques. But the typical way we study high energy hard X-rays above 10 kV to 100 kV up until now has been the coded masks. The coded mask is essentially just a plate with a random pattern of holes which allow X-rays to pass through and be detected in a position-sensitive detector down here. Such an instrument has a very nice property that it can be made wide field. You can look over a relatively wide, big area in the sky, so you can detect many sources simultaneously, but it is not a focusing detector. Essentially, all the sources are mixed together on your detector, and you have to devise algorithms to disentangle the photons from the different sources, and it's precisely that project which Sylvia and I have been addressing in my study here over the last 3 months. In the same energy range, 10 kV to 100 kV, we now have the multi-layer telescopes. The classical X-ray telescopes used a thin gold layer or platinum layer to reflect the X-rays, and they can only be X-rays can only be reflected with very small angles, what we call grazing incidence. So, and this is true also for the multi-layer telescopes. But the idea of the multi-layer telescopes is that if you put many layers of alternating layers of a light and a heavy material, you can create some kind of artificial crystal structure which will, where the different layers will cooperate in producing stronger reflections. You will make coherent reflections, and this is how it is possible to generate artificial mirrors. There will be hundreds of layers, or there are hundreds of layers in these artificial mirrors, which can reflect X-rays today up to about 80 keV, and maybe in a few years up to 300 or maybe even 500 keV. 300 keV seems to be technically within reach today, but it's not made. But the New Star mission, which was launched by NASA last year and carried X-ray telescopes developed at my institute in Copenhagen, is actually already getting the first focused images in the range above 10 keV. When we go higher, 100 keV to 1 MeV, then, as I already mentioned a couple of times, coded masks are today the technique which can be used and is used, and it is used very much, say, on the integral satellite, where we have 3 coded mask instruments, speed spectral imager, which with a very heavy mask and also very big detectors can image up to 10 MeV, but with limited angular resolution. Then the EVIS, which is another very big instrument on integrals, which work in the range up to, say, essentially up to 500 keV or so, a few hundred keV, and then Gamma-X, an instrument with which I have been strongly involved, which is operating from 3 keV up to 30 keV. But all of these 3 instruments are coded mask instruments with large fields of view, relatively large fields of view, and normally will observe many sources simultaneously. What we could hope for in the future would be possibly to make a telescope where we use crystals to focus the gamma rays. Such studies have been made, proposals have been made for such missions to ESA, but was not selected, and was not selected essentially because they were not yet good enough. I mean, the efficiency of such telescopes, it's hard to get high efficiency, and because the diffraction angle for gamma rays in the range of several hundred keV are very small, the telescopes become very, very large. I mean, they should be maybe 30 meter lengths or 100 meter lengths. So it is missions such missions have been discussed with separate satellites, one satellite carrying the mirror and another satellite carrying the detectors, so flying information. So it is a complicated thing and has not yet been realized, but we are allowed to dream. And now we come to this nasty range, 1 MeV to 30 MeV, where the best technique is the Compton telescope. Let me first describe what the Compton telescope is. It is a telescope where the photon is expected to come in and make a Compton scatter in one detector and then be detected and absorbed in another detector down here. And if this is actually what happens, we cannot be sure that is what happens, but if that is happening, then you can look at the energy deposits in these two, and from the two energy deposits you can see how much the photon lost in the first interaction, and therefore you know by which angle the photon was scattered. And if you also know, because you know where it hit here and where it hit there, the direction of this line here, then you can say, well, the photon came from somewhere on this cone. A cone has an opening angle corresponding to the scatter angle of the first interaction, and then the direction of the axis of the cone is given by the position of the second interaction and the position of the first interaction. It is, of course, a quite complicated detection system and not giving very nice pictures, but it works, and the Comtel telescope which flew on the NASA Gamma-Ray Observatory between 1991 and 2000, and was successful and did in fact detect the first. Well, it was not the first detection, but it could for the first time make maps of the sky in this energy range. And again, the interest in this range is very high because you can see nuclear lines there, and that can tell you a lot about what is happening in the objects you are studying. This is again just an illustration of the Compton geometry: a scatter point, a detection point, a line giving you the axis of the cone, and the scatter energy, the detection energy give you the opening angle of the cone, and so you draw a circle. And when you have many, many circles, if there was only one source in the sky, all the circles would nicely coincide or go through this point, and this unique source point. In reality, there are lots of sources, and there is a diffuse background, and there is the instrumental background, which make the picture much more messy, but doable. For the future, we could hope to make an advanced Compton telescope where we use more modern detectors than the detectors used in the first Compton. One possibility is to use germanium detectors, which nowadays with the modern electronics can be made so that they have three-dimensional position resolution, and therefore you can get, within a small volume, you can get accurate directions, and also you can handle multiple scatterings, which in some cases can give you very unique information about the direction. So this is because of the much improved energy resolution of the germanium detector and the much improved position resolution, one can do much improved construction of the circles, and this means that actually the background will be reduced a lot compared to the background which were relevant for Compton, which is the only instrument of this type which has flown so far. But it is an expensive, complex instrument which have not yet been realized. You can today also imagine several other combination detectors. There are the germanium detectors are a bit unpleasant because they need to be cooled to operate well. Today you can make room temperature, semiconductor detectors, and this is a work which is also going on in Copenhagen. And they can also be made with three-dimensional position resolution, and this could possibly lead to a simpler overall design, but it is still, it's a complicated instrument. You cannot make a small you cannot make a light instrument because Compton interactions have very low cross section. So if you have a very small instrument, you will not catch any photons. You will need an instrument with several or many kilograms of detector, and that is going to be expensive. Now we come to a little easier range. When we come above 30 MeV, then pair creation is dominating, and pair creation has higher cross-section, and the electrons travel relatively in straight lines, and therefore you can use the direction of the two electrons which come out from the pair creation process. If you can measure those directions well, you can point back to the source in the sky. So instead of having a circle which you have in the Compton telescope, you actually do have a little spot. The spot is not so small, unfortunately. I mean, the spot is typically a degree or so in diameter. For the single electron, it is even larger than that. So it's not extremely good position resolution you can have, but in the best cases, it is in the range of, say, half a degree or so. A little less than that, 10 nanometers. But it's only for very few sources. The higher, one way to get good position resolution is to look at high energy photons. But there are only few sources which emit very high energy photons. So if you have a photon of, say, 50 GeV, then the electrons are very difficult to scatter, so they travel straight through many, many layers of your position-sensitive detectors, and you can get a good direction. But if you are looking at 30 MeV gamma rays, what you get out is maybe 15 MeV electrons, and they scatter a lot, and so your position resolution is But the Fermi mission has really broken through a barrier of what I just mentioned. What the detection technique again is that you have converter foils, thin lead foils in which the pair creation will take place, and following each of these relatively thin plates, you have a crossed pair of silicon strip detectors which can give you very precise positions of the traversing electrons. And you want to divide this converter into many thin plates because of this multiple scattering problem. If you have a thick plate, the electron will have scattered before it comes out of your lead plate, and so even the first measurements or the first few measurements will not give you a good direction. This is why these instruments are always constructed with quite thin lead foils, so that you can hope to have several measurements of the electron track before it is scattered. You can see that it's indicated here that it is scattered before it is scattered too much. Fermi has been an extremely successful mission. One of the things where it has really made its mark is that it has discovered a large number of pulsars in the millisecond range. And millisecond pulsars were known before Fermi and had mostly been found in radio and then detected in X-rays afterwards. But it came as a surprise that Fermi detected a large number of these known millisecond pulsars at the high energies, at these very high energies, and moreover that Fermi detected a number of millisecond pulsars which the radio people had not seen. So they emit in gamma rays, not in radio. So this has been a remarkable success of Fermi. This is an old slide, and there are many more millisecond pulsars now. But the point is that there is suddenly a new window of detecting millisecond pulsars, and this means that we know now that the origin of millisecond pulsars can produce such systems close very rapidly spinning neutron stars which will emit essentially only in gamma rays. In some cases, the radio people have found the millisecond pulsars after the gamma ray, but I think there are, in fact, cases where the radio people have not been able to see pulsations in the radio signal. So it is a very interesting result from Fermi that you have these strong pulsations in the very high energy above 100 MeV essentially. So there's a nice synergy between gamma ray astronomy and radio astronomy in this study of pulsars. And you can see that you use the millisecond pulsars as celestial GPS if you want, because if you measure the rate of a distant millisecond pulsar, you know how rapidly you move towards this one, and so instantly you could build a GPS independent of but you need to be able to detect X-rays and gamma rays, and that's so it's maybe not the simplest GPS receiver to make. Now I come to this band about 100 GeV, where in my view, the most important development has happened in the gamma ray astronomy within the last 20 years, namely that one has made very accurate instruments which can pinpoint sources at energies above 100 GeV. And the idea is that the gamma ray quantum comes in and hits a nitrogen or an oxygen nucleus, and with a very low probability, the air creation cross-section is low, but anyway, it is creating a pair, and these electrons has very high energy in themselves, so they soon produce other gamma rays which produce new pairs. So you have an air shower consisting only of electrons coming down, and these electrons are so fast that they emit Cherenkov emission in the air, thin air, and this you can detect. Of course, your background is that you have about 100 or 1,000 times as many particles as you have electrons. So you need to have a very efficient discrimination against particles. And the way you discriminate, there are several ways, but first of all you can say that typically the air showers which comes from an incoming atomic nucleus will start higher in the atmosphere than the gamma rays penetrate deeper. And then another thing is also that there are created muons in these showers, and there are essentially no muons over here. So there are muons here, and these muons penetrate to the ground and detect them and say, this was not an interesting event because it contains muons. It is an old story, this air Cherenkov. I think it was already Jelly who was one of the studied Cherenkov radiation early on, and he suggested that one should look for these air showers, Cherenkov emission from air showers. And this was done as early as 1967 by Trevor Weeks in Arizona. He got some military searchlights, good nice, good 1.5 meter or whatever it was, mirrors, and put them up. And in fact, each of these mirrors had a phototube at focus, and then he could count coincidences. So that the noise in one phototube was not enough to trigger that. He thought he had an air shower, but when he had simultaneous signals in the tube, then he knew he had something coming in from the atmosphere. And with this type of instruments, which was also built in the Soviet Union and other places, the first detections of the Trap Nebula. Of course, the Trap Nebula always pops up. It's such a nice source. But also of extragalactic sources were seen. Say Mercurian 421 for one was seen at these very, very high energy. But the real breakthrough came, say, about 20 years ago, or maybe it's not even 20, maybe less than that. But it was with the development of the HESS telescopes by the German group which the HESS telescope was put up in Namibia and on a high plateau. And they produced these nice slides which show what happens. Here's a gamma ray coming in. It creates a particle shower at an altitude of about 10 kilometers. And then the air showers will generate Cherenkov light, and the Cherenkov light penetrates to the ground, and from such a shower at the smallest energies which can be detected. The shower is not the shower, but the Cherenkov light is illuminating an area of some 200 meters diameter. So then you put up some mirror telescopes within that 200 meter light area, or you wait when you have put the telescope that as photon comes in towards your telescope system, and then you will get simultaneous signal. So the trick which was first implemented in HESS in a large scale was to make a focal plane with many pixels, so that they could, in fact, image the air shower and image the and it would give a little elongated strip in each of the telescopes, and by looking at the intersection of these strips, you can get a quite accurate position on the sky, a position with an accuracy of a few arc minutes. So this system is much better than Fermi. It's giving much higher resolution, and it has allowed to study morphology of supernova remnants, for instance, and other active regions with much better detail than possible with the Fermi type of instruments. So you can see here's an example of one of the HESS focal planes. You can see it's a large thing, and now there is some 900 phototubes there. And again, also you can imagine this can only be done today. Trevor Weeks could not have done it in 1967 because the electronics which is required to run this was not available. But this has come along with the development of microelectronics, that you can do this and you can handle this type of instrument. And then this is what you see in your when you display what is happening. You see these stripes here is just one air shower, and this is a nice electron air shower, whereas the circles which we had, if we just go back here and run it again, the circles which are so very beautiful to look at, they are actually muons which come all the way down and hit your mirror and produce a nice ring of or a nice cone of Cherenkov light, which will be imaged as a ring by the optics. The way the telescope system with the 4 telescope works is that you have this image in 4 telescopes, and in each of them the direction of this stripe is slightly different, and when you make the intersection of these lines, you get a point on the stripe which is defined with an accuracy of a few arc minutes. So this is a very beautiful technique. And this of course, other people than the German group were working on this. The Germans were the first, and also, of course, the Germans was an inspiration for a lot of people. So there are many other systems which work like this today. In fact, this Veritas in Arizona, it's the same site that was used for the 1967. So 40 years later, it was larger, much larger mirror. You can see it's maybe 10-meter diameter mirrors and much more complex focal plane instrumentation. And there's also one on La Palma, Magic, and which had larger mirrors than both Hess and Veritas, but fewer, only 2 mirrors. So now you can, in fact, look at the sources of ultra-high energies with unlimited resolution. Here is an image of the supernova 1006, which was imaged by X and Gamma-Ray, but was also imaged by the Japanese satellite. Oh, that's right. Disappeared from my mind. The Japanese were the first to make this kind of image, as far as I'm aware, supernova 1006, where you have a supernova remnant, which is known from the optical studies, and it is known that these are the edges of a relatively spherical supernova shell, which is hitting the interstellar medium, interacting with the interstellar medium. Better take a bit of water. So one of the, I must say personally, I have been very, very happy to see these images, because the typical image at 100 GeV or TeV, 1000 GeV, is not point sources. It's extended sources. And this suits me well, because I started out my career studying cosmic rays. And one of the results, we made an instrument which determined the composition, the chemical composition of the cosmic radiation. We hoped to demonstrate that cosmic rays came from supernovae, because everybody believed that cosmic rays came from supernovae. And we worked hard for 10 years, and the result was that cosmic rays look like the solar system. It's a mixture of everything, and it's absolutely not supernova material. So cosmic rays do not come directly from supernova, at least not the material. So it has been then also clear that you need something else to accelerate the cosmic rays than just the initial supernova explosion. And collision, it has been speculated for a long time that acceleration of particles took place where you had collision of shock waves between fast-moving plasma and slow plasma. And this is very nicely demonstrated here, and it's also demonstrated that where you have the energetic particles is not where the supernova. The supernova is somewhere in here, and it's very unlikely that much material of supernova origin. It is not the material itself which moves out there necessarily. It is the shock wave, the compression wave, which moves through space. And that is where you have the acceleration of high energy particles, and therefore it is not so unnatural that it is not just a clean fingerprint of the material which came out of supernova you find in the cosmic radiation. And there are many also just pulsar wind nebula, another case where you have strong stellar winds, can also produce these ultra high energy photons. And
So we don't need an explosion of the magnitude of a supernova to make ultra-high energy cosmic rays. A completely different approach to detection of photons and particles was taken in Los Alamos, where they used a big water reservoir tank, which was not used for anything else, as a particle detector at ground level. So now they're not looking at things happening up in the sky, they're happening at the particles coming down to the ground. And this, of course, means that they have an enormous background of particles. But again, they can distinguish. This is actually a view of the pond, and you can see that there's a rubber boat sailing around there. And then you have full body glass all over the place, detecting the light from the Cherenkov emission in the water. These are particles coming all the way down to the ground, but Los Alamos is at some altitude, and you have then a Cherenkov emission in the water. If what comes in is electrons or gamma rays, they will stop within the first few meters. You get most of your emission in the first few meters of water. If it is a muon, it will go all the way through, and you will get the signal both in the top and in the bottom layer. So essentially, if they want to look for gamma rays, they look. They try to eliminate all events which trigger the bottom layer, and with that, they can map the sky also and detect gamma ray sources. And one of the advantages of this technique compared to the Air Cherenkov telescope is that this is wide field. It's looking at all the sky. Anything which is so it has a much wider field of view than the Cherenkov telescopes, which are optical scenes which with a few degrees field of view. So it has its drawbacks because background is set high, so you can only see bright sources. But it also has its advantages because it's looking at the whole sky. Half of the sky. And so you have here the angular resolution of the Cherenkov telescopes is like 2.5 minutes, and the Milagro telescope is like 1.5 degrees. So it's typically corresponds to what Fahrenheit is doing, which is not bad. And then field of view 3 to 5 degrees, and here it is 40 degrees. Threshold is higher for Milagro because it can also the particles have to come down. So has a higher threshold. Resolution is worse, but also the duty cycle is higher. This is another point where it has some advantage, because Air Cherenkov, of course, needs dark nights. No other. So they have a limited duty cycle, whereas this is looking at particles and can look day and night. So it's essentially. So it's very good for unbiased surveys, very good for transit objects, gamma ray bursts, if they, and I don't think they have seen gamma ray bursts yet. So it's not, gamma ray bursts are not typical emitters of many TeV emission. That's not their business. So I must say I'm personally very much interested in the next generation of this Milagro thing, which is a high altitude water Cherenkov system, which is being built in Sierra Negra in Mexico, and it has moved up to about 4,100 meters instead of the 2,300 of Los Alamos. And this means that they can detect lower energy showers because they can better penetrate to 4,000 meters than to 2,000 meters. And because of much improved detectors, they can also detect smaller stuff. So it is foreseen that when this thing comes really online, that we will have a great step forward in this technique. And also, again, with my old love of cosmic ray particles, I'm very curious to see what they find in terms of cosmic ray particle. Are there non-uniformities in the directions? Are there preferred directions for these high-energy cosmic rays? Or are they completely washed out by the magnetic field in the galaxy? So, I'm coming to the end. Gamma-ray astronomy is still a young science, about 50 years ago, and I'm quite sure that the next 50 years will bring as many nice surprises as the first 50 years. Thank you.
Thanks, Niels, for this nice presentation. It's now time for questions. Do we have any questions from them?
If I understood a little, the path of the gamma photon is unique when go to the detection, or there are...
The bulk of them are what is making photon scatters or
Just in the slide of the Fermi, there is an image that
okay, yes.
can help to explain that. I mean,
we go back to Fermi. Yeah, we were here.
yes, my question is, there are red points, these red points in the other slide,
Yeah.
On the other one, is the one of
the previous one,
The previous
next
one.
The next one.
or the
That
next
one.
one.
Yes.
Yeah.
The advanced quantum telescope there.
The blue line is the gamma,
Yeah.
and the red points are the path of the
Interaction
gamma.
points. Yes.
So my question is if this path is unique and you can directly correlate the point of the production of this gamma photon.
No, what you can say is that when you have several scanners, then the direction of the incoming photon, you can find that if you can actually see the electron being scattered. I think also in this case you know more because you have one scattering plane here defined by the 3 points. So I think actually the probability that the photon comes from a plane is larger. So this circuit is not uniformly populated, but I would not think that this is the major advantage. The point is just that when you are talking about these more advanced telescopes, they will be designed so that they produce a better confinement of the photons. What happens is that if what will easily happen in say computers is that you have a scatter and another scatter, and then the photon runs out of your second detector, and so you misinterpret the energy of the incoming photon, and therefore you misinterpret the angle, and so you're missing your source. So you don't back project to your source if you don't get the first angle right. Now, as soon as you have 3, there are constraints about you know from this scatter that you can solve completely for the energy, and you can therefore be sure that you have seen it all. You have all it, more so. So you can eliminate many of the cases when you have 3 scatters that where the photon runs out here. It could happen. It could happen scatter 1, 2, 3 times and then run out. But this would then leave you with energy deposits which would not fit the scattering angles, and so you can develop. So as these instruments are developed and get larger, you will also get cleaner results, because first of all you will catch more photons and be sure that just the simple probability that you have gotten all the energy is higher. But also, if you have several scatterings, then you can verify that the scattering angles are consistent with this being a photon which was finally completely absorbed.
You have mentioned talking about blue star. Yeah. With this multi-layer mirrors, maybe we could go up to 300 keV. Yeah. But what about the focal length of the telescope? Should be much higher than for blue stars. Could it still be fitted into a single, not formation telescope, but
I think that the idea is if you want to go to say 300 kV, I think you can still do it with but you will need say 20 meters. But this you could still manage to do with a boom. But if you go higher, if you go to 500 kV, so I think a boom is probably going to be a very difficult animal to control in space. Maybe in the future we can make what I would call active booms. Booms where the joints are trying to compensate for and then out. I would say that's it. But the important thing about booms is that they vibrate. And if you make them active, so that they had active band, actually they were sensing that they were oscillating, and they were trying to damp out these oscillations. I think this can be done, and this may be simpler than having the formation flag. I was surprised, I've been involved in some of these studies, and I was surprised to hear that formation flying can be done not only for missions flying at the Lagrange point. They can also be done in the elliptical orbit. So there's a good fraction of the elliptical orbit where the gravity gradient is small between the two satellites. It's small enough that you can, with small rocket motors, manageable rocket motors, can keep them informed. But still, it is a complicated business, that formation. And whether that would be the preferred option or a boom which may then be a more complex boom with some active damping of vibrations. I don't know. I mean, that's until we have say sufficient pressure for developing this type of mission, we will not know, because there are certainly many technical problems on the way. Once it's done, and then you can just do it. But to get there is quite difficult, and it's not quite transparent where the difficulties are.
Yes, probably with this question, when do you think we'll be able to focus the LTV photons with a resolution similar to the optical telescopes? Is just a dream? Will you do that in the future?
No, I think MEV photons they may be focused say with a resolution of maybe arc minutes, but an optical telescope I don't see any technique which can do it. You can make all kinds of fancy dreaming, but I don't think that any of these are within technological reach. Whereas I think a lower telescope could focus at least up to 500 keV and could give you something like an arc-minute resolution, which would still be a very nice thing to have. But now, of course, 20 years ago, when the 511 keV, half MeV emission from the galactic center was a big thing, and people were discussing whether it was a point source or because it was there, or a fuse source and so on. Then it would still be interesting to look with our telescope at the galactic center. But today, I think we know pretty well it is a diffuse source. And if it is a diffuse source, then the large telescope will not work because it only has a field of view of a square arc-minute or a few square arc-minutes. So it can map it, but it's not really going to give us a big gain in sensitivity if the source is diffuse. So I would say our telescopes also have their limitations. And I have been a great fan of our telescopes, but I'm not sure that they will ever be materialized.
Okay, any last question? I think I have one. You haven't not talked about the time scales and the development of this kind of. How long it takes to make reality one of this kind of projects? How many people are involved in?
Yeah, I mean, you can. I think this is more a matter of, say, science, politics, because you could see that the Americans could do something absolutely extraordinary, namely flying to the moon, in less than 10 years, if they put a whole nation onto it. But we don't put a whole nation onto gamma-ray astronomy. Of course we don't do that anymore. And so if we then look at the realistic time scales for space missions in ESA, we can say, well, it's 10 to 15 years. And as far as I can see, a telescope of this type, maybe not with germanium, but with cadmium-zinc telluride detectors and so on, could be proposed, say, for the next medium mission. So then we would talk about 2028 or 2030. So we're talking about 15 years. So you're young enough to see that.
Yeah, but we need to convince the committees that this is really the science which are being done, and
Yeah.
we have to convince
And
the politicians to get the money to the countries. And well,
and of course, this is a difficult part because there are other players in the game,
Yeah.
and they have also good ideas, and they would also love to get that mission in 2028. So the competition is quite hard, and you need to be able to demonstrate that you have something which can really do something very unique, very good, in order to be successful. Otherwise, no chance.
okay, well, we should give thanks again to Niels for this really nice presentation.